Hello everyone. On this video we will be looking at standard unit vectors. Okay, so to get started, I will show you what a standard unit vector looks like. Okay, so it's our I vector. That's equal to 0.10, and our J vector is the vector 0, 1. So you have 1, 0, and 0, 1, which is how it would look in 2 dimensions. But we have our I vector is 1, 0, 0. Our J vector is 0, 1, 0. And our K vector is 0, 0, 1. And that's in 3 dimensions. Okay, so those are our unit vectors. Okay. Now, what are they used for? I'm glad you asked. These vectors can be used to represent any vectors. Be used to represent any vector. Okay, so how? Let's say if we had a vector B. Okay, and we know that vector B in 2 dimensions has 2 components. That's value number 1 and component number 2. Okay, so we can actually separate those into 2 terms. So if you have component number 1, 0, and 0, component number 2. Okay, now if you add those together, you get component 1 plus 0 is B1, component 2 plus 0 is B2. So all we did was spread it out a little. Okay, so now we can actually factor out those known components. So we have component number 1 times our unit vector plus component number 2 times our J vector. Okay, so we can actually rewrite this as our B vector is equal to component number 1 times the I unit vector plus component number 2 times the J vector, unit vector. And of course, that's 2 dimensions. But if we had 3 dimensions, of course, it's pretty much the exact same thing. Okay, we had our B unit vector, or B vector in 3 dimensions. We know we have our first component, our second component, and our third component. Which, just like up here, we can separate those into 3 vector terms. Now I'll put that underneath. Okay, so we have, bring that up a little. Component number 1, 0, 0, plus 0, component 2, 0, plus 0, 0, component 3. Okay, and just like here, we can factor out those components and leave just unit vectors. Okay, so if we factor out component number 1, that leaves 0, 1, 0, 0. Jumping ahead a little bit. If we factor out component number 2, that leaves us with 0, 1, 0. And if we factor out component number 3, that leaves us with 0, 0, 1. All right, so just like our 2 dimensions, that now leaves us with our I, J, and K unit vectors. So we see that our B vector can equal component number 1 times the I vector plus component number 2 times the J vector plus component number 3 times the K vector. Of course, this is our 3-dimensional explanation. That kind of ends that one. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and go to our next page. Okay, so what that means is that, for example, if we have the 2-dimensional vector 2, 4, we can write that as 2i plus 4 times j vector. Or even if we have the unit vector 2, 4, not unit vector, the vector 2, 4, negative 7. We can write that as 2i plus 4 times j vector minus 7 times the k vector. Okay. So it really gives us another way to write our vectors. Okay. Now, quick note here. So if we have some vector, we'll call a, b, whichever variable you want to use, that's component number 1 times the I unit vector plus component number 2 times the j unit vector plus component number 3 times the k unit vector is called the linear combination of I vector, j unit vector, and k unit vector. Okay, so when you see a problem and they say solve it and give the answer as a linear combination, then you'd have to give it as the I, j, and k, or I and j if it's just 2 dimensions. Okay, now in 2 dimensions, the scalars a number 1 and component number 2 are called the horizontal and vertical components of A, or A vector. All right, so just a little bit of terminology to help you kind of go through everything. All right. So let's say if we do a quick example, kind of help you get familiar with the new terminology. What if we wanted to find the magnitude of v vector equals 6 times I vector minus 5 times j vector? All right. So to solve that one, we have to remember that the magnitude of v vector is equal to the square root of the first component squared plus the second component squared. Okay, so That's our formula. Remember, that is not absolute value. So try to remember that. Okay, so if our v vector is equal to 6 times I vector minus 5 times the j vector, remember the 6, that's your A first component, and your second component is the negative 5. Okay, so if we plug it into that formula, you have the square root of 6 squared plus negative 5 squared. Okay, so that's equal to the square root of 36 plus 25, which means the magnitude of our vector is square root of 61. Okay, so it's all solved the exact same way, just written a little bit differently. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next page. Okay, now in this, we're going to look at the theorem of the unit vector in the direction of our b vector. So what we're going to do is we're going to create a unit vector that's in the very same direction of our whatever given vector we have. Okay, so let's say if b is a non-zero vector in the plane. Okay, be 2 dimensions, 3 dimensions, doesn't matter. It's just in a plane. Then the unit vector u equals the vector of b over the magnitude of vector b. That's our unit vector. Got my little vector symbol. Okay. But we can also rewrite it as 1 over the magnitude of vector b times vector b. Okay. Now, I didn't use the multiplication dot there because we do have a section coming up called the dot product, so we're going to need that dot for something else. That's why I didn't use the dot and I used the parentheses. Okay, so the unit vector u equals 1 over the magnitude of b vector times b vector has a length of 1 and the same direction as our b vector. Okay, so how do we know that? Well, we'll go ahead and prove it. Okay, well, one thing that we can say for certainty is we know that 1 over the magnitude of b vector is positive. Okay, how do we know that? Because the magnitude of b vector is equal to the square root of the first component squared plus the second component squared. So even if the first and second component happen to be negative, once you square them, they'll become positive. So you have 2 positive numbers you're adding together and the square root of that positive number. So it's always going to be positive. Okay, well, what else? Let's say since u equals 1 over the magnitude of b vector times the actual B vector, okay, we can say that, or we can know that the U vector will have the same direction as B vector because it's just a scalar multiple of the B vector. Okay, think about it this way. The magnitude, or 1 divided by the magnitude, you end up with a scalar. So you have 1 divided by some number, square root of some number. You're just getting a real number and multiplying it to your vector. So it's going to be the same direction because it's just a scalar multiple. Okay, so we know that it's the same direction as B. Now we have to prove that it has a length of 1. Okay, so to prove that the magnitude is equal to 1, okay, we know just from looking that U, that's equal to the B vector over the magnitude of the B vector. So that means if we take the magnitude of both sides, we have the magnitude of the U vector, which equals the magnitude of the B vector divided by the magnitude of the B vector and all that, the magnitude of the entire thing. Okay. Now the one thing we know is that if we have the magnitude of the B vector, we're just going to end up with a scalar. If we take the magnitude of a scalar, that's just the same thing. Because the magnitude of 1/2 is just going to be 1/2. Okay, so that's why we can actually break that up and say that the magnitude of our B vector up top is going to be divided by the same magnitude of the B vector at the bottom, which anything divided by itself, of course, is just equal to 1. All right, so that's how we know that this theorem is actually true. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next page. Okay, so now we're going to look at unit vectors as far as visually. So you can see exactly what they look like. Now in 2 dimensions, of course, we have our XY axis. We have our X, and we have our Y. Okay, so if we get our horizontal vector, that's our I vector, which is equal to 1, 0. And our vertical unit vector, that's our J vector. So our J vector, which is 0, 1. Okay, so starting at 0, and our terminal point is 1, 0. So starting at the 0 or the origin, our terminal vector is 0, 1. I mean terminal point. Okay, now in 3 dimensions, we have, remember, our X, Y, and Z. The same here for our I vector, or I unit vector. That's 1, 0, 0. Now for our y axis, we have our j unit vector. So our j unit vector is 0, 1, 0, where x is 0, y is 1, z is 0. So for our k unit vector, our k unit vector is 0, 0, 1. Okay, so that's how the unit vectors would look visually. Okay, so these are your standard unit vectors. Okay, a couple of things you need to know about them is, by definition, the magnitude of a unit vector is actually just the square root of the first component squared plus the second component squared plus the third component squared. Okay. Now, if you did everything correctly, when you add those all together, you should get the square root of 1, which is just 1. Okay, and the next thing that comes in handy is the fact that two non-zero vectors, we'll call it our unit vector and our a vector, are parallel if there is some scalar, and we'll call that scalar c, such that u is equal to some scalar times the a vector, or u vector is equal to some scalar times the a vector, or even some scalar times the u vector is equal to the a vector. It could go either way. Okay, so for example, u vector is equal to 2 times the a vector. U and a would be parallel. Or let's say 1/2 of the u vector is equal to the a vector, then u and a would be parallel. Or even if the u vector is just equal to the negative a vector, u and a would be parallel. Okay, so that's something that would be pretty handy to know. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next page. All right, so for example, what if we let a vector represent a vector with the initial point to -5 and terminal point of -1, 3. But wait, there's more. Also, let b vector equals 2i vector minus j vector. Okay, so what we want to do is we want to find the a vector, and w equals 2 times the a vector minus 3 times b vector. And we want to write both as a linear combination of I and j vectors. All right. So let's go ahead and solve these. Okay. So if we have our 2 points, we have our initial point and terminal point. We'll say that our initial point, we'll call that point P. And our terminal point, we'll call that point Q. Okay, so of course this is our initial and terminal points. Okay, now that means this is our first component, and this is our second component of point P, and this is our first component and our second component of point Q. Okay, so if we know that A is equal to the directed line segment PQ, or P2Q, okay, we also know that vector A will be equal to Q1 minus component P number 1 and Q number 2 minus component P number 2. Okay? Because remember, we're just given 2 points. We have to use those 2 points to find our vector A. They gave us B, but we still have to find vector A, so that's what we're doing now. Okay, so vector A is equal to component Q number 1 and P number 1, so you have -1 minus 2. So -1 minus 2, we have 3 minus -5. Okay, once you plug in those values. So that means that vector A is equal to -3, 8. Okay, but you're not quite done yet, because remember, they want it written as a linear combination of I and j. So that means that vector A is equal to -3 times vector I plus 8 times vector j. Okay. Always remember, if they ask for that linear combination, to put your answer like this, because if you leave it like this, you'll have it marked wrong after doing all of that work. All right. Now we want to solve for our W, or W vector. Okay, so W vector is equal to 2 times A vector minus 3 times B vector. Okay, so that means W vector is equal to 2 times A vector, which is -3I vector plus 8 times the J vector, minus 3 times the B vector, which, going back up here, is 2 times the I vector minus the J vector. Okay, so all we do really here is just go ahead and distribute our scalars. Okay, so W vector is equal to 2 times -3 is -6I. I vector. 2 times 8 is plus 16 J vector. Minus -3 plus 2, well, times 2 is -6 I vector times I vector, plus 3 times your J vector. Yeah, and even though these are not variables, your I's and J's aren't variables, when you're combining like terms, you pretty much treat them like variables. So you combine your 2 I terms and your 2 J vector terms. Okay, so that means that your W vector, you have -6I, -6I, is negative 12 I vector. So move that up some. Plus 16 plus 3 is 19, so you have 19 times j vector. All right. So that is how you would solve that one. Okay, so again, if you're still writing, feel free to press pause, but we're going to go ahead and do one more example. Okay, so for example, what if we wanted to find the unit vector for, let's say, b vector is equal to negative 2, 5, and verify that it has a length or magnitude of 1. Okay, so you may have a problem where it say find out or verify that it has a magnitude of 1, same thing. All right, so first thing we want to do is we want to find our unit vector. Can't do anything without the unit vector. So we have our unit vector, which we know is equal to our vector divided by the magnitude of that vector. Or we can make it 1 over the magnitude times that vector. Okay, so we know that our b vector is equal to negative 2, 5. That means that's our the first component and our second component. Okay, so we know that our u vector is equal to, we'll use this one because it's a little bit easier to work with, at least for me. If you want to use this one, that's perfectly okay. Okay, so you have 1 over the magnitude of the vector. Remember, that's just the square root of the first component squared plus the second component squared. And that's times the b vector, which is just negative 2, 5. Okay, so remember, the magnitude of the b vector is the square root of the first component squared plus the second component squared. I do that because I hate to see anyone think that that's absolute value, and it's not. All right, so now that we have that, we can go ahead and solve this part of it. That means our unit vector will equal 1 over, you have negative 2 squared, which is 4, and you have 5 squared, which is 25, so you have the square root of 29. So 1 over the square root of 29 times the vector b. Okay, so that just means that our u vector is equal to, remember you can just multiply that scalar to each one of those, so you have negative 2 over square root of 29, and you have 5 over the square root of 29 as your unit vector. All right, so now we just have to verify that this unit vector has a length of 1. Okay, so we verify the length of 1. Okay, so that means that the magnitude of our unit vector is equal to the first component of our unit vector squared plus the second component of our unit vector squared. Okay, so that means this is our first component and this is our second component of the unit vector. So that gives us square root of -2 over square root of 29 squared plus 5 over the square root of 29 squared. Okay, so we go ahead and simplify that. -2 squared is 4. Square root of 29 squared is 29. Plus 5 squared is 25. Square root of 29 squared is 29. So that actually leaves us 4 plus 25 is 29. So we have the square root of 29 over 29, which is the square root of 1, which is just 1. Okay, so we found our unit vector, and we verified that that unit vector has a magnitude of 1. All right, so hopefully that made sense, and I will see you on the next video.